Okay, guys, so now after teaching you uh, how to model a dynamical system, I meant mechanical, driving nonlinear differential equation, and then linearizing around the coupling point, and then transferring everything to the MATLAB using the ODE, comparing nonlinear with linear differential equation, and then how to make a movie of that. And then we saw that in some differential equation, so you cannot solve it because in the right hand side or the force or excitation, they are impulse or discontinuous function that you have to transfer everything from time domain to frequency domain or S domain. And that's why I introduced you the Laplace table. And now it's time that we go to the block diagram, because theoretically in this class and in MATLAB and Simulink, that I'm going to share the files with you. Okay, so we're gonna model the systems through block diagrams. So as I told you, so if this is the input of the system, x of s, because now we are working only in S domain, frequency domain. If this is the controller, that I'm going to just give you hints at the end of this semester, okay? That's it. And because the control part goes to ME430 mainly, but I'm just going to hint what is that. So this is the controller of the system, and this is the open loop transfer function of the system, G of S. I'm going to teach one by one. And this is the output of the system, Y of S, the real output of the system. This is your desired input, desired input that you want your system follow that. Because that you want to have 78 degree in your room temperature. This is that you desire that you want to have. So you put the controller in the room through a box. I bet that you have seen a million times. This gonna affect, send a signal, U of S signal, control signal to the plant. Your plant is room space. The dynamics of that, okay, temperature wise. I'm gonna teach that eventually in the modeling phase. And then it sends out the temperature to your room and you feel it. When I say you feel it, you can measure it also. And the controller of the room does it. And it sends this signal, Y of S, to a sensor. Okay, sensor, say temperature sensor, H of S. And then this being compared with your desired input. So your output, Y of S, is being compared with the desired input. This generates the error signal, E of S. E of S goes to the controller based on this error signal. For example, if you want to have 78 degree, but your room, the real output of the system temperature is, name it, 74 Fahrenheit. So you see that there is error signal here, that's right? So for this moment, the error signal of your system, E of T, just a moment, I'm backing to the T, is, see, plus 78 minus 74. So you have 4 degrees until you reach your desired input, guys. So based on this error signal, controller send the signal, okay, to the heat source of your home, okay, and then your home runs the differential equation. I'm just saying simply. And this again sends out the real output of the system, real temperature. And this loop, this feedback loop, we are saying feedback loop. Feedback, because you are feeding back the real output to be compared with the input of the system. Clear, guys? Yes? This feedback loop is being ran until your error signal E of t becomes 0. And you reach the temperature that you want. Another example of this, I'm pretty sure that you have car, and most of the cars you have, they have the cruise. Yes? Cruise system. You say that, okay, I'm in a highway, I don't want to push the gas pedal by my leg. I want to just relax. So I want to have the velocity of my car to be 65 miles per hour. So here is the model of your car. Model of your car, your plant is car. This is that. So, but the real output of, the current velocity of your car is, I don't know, say 56 miles per hour. So this being sensed by the sensor in your car, being compared with your wish list of the velocity, sends your error signal to the control unit of your car. You do have in your car. In the modern car, they have it. This is gonna send, instead of your leg that you're pushing the gas pedal, this sends more fuel to the engine, to your plant, your car, and it produces new velocity until this loop is being repeated until the velocity is 65 miles per hour. And this is how simple like that. This is how your car cruise system works. Based on this block diagram. Is the control input to the car. Okay, guys, it's a good question. What's your name? Christian. Suppose that in the old cars, the control input to the car is your leg. You are pushing the gas pedal more. You are entering more fuel into the engine, so your car speed up. Yes? So U of S is your leg that you are pushing the car. Yeah, the car gas pedal. See what I'm saying? But in the cruise system, you don't need to do that. You just set your wish list of the velocity, your desired velocity, and then the cruise system, the control unit of your car, instead of your leg, send the control signal to the car. See what I'm saying? On the other hand, opening the fuel tank more, that the fuel goes to the engine and you have the desirable velocity. See what I'm saying? Yes? Yes, Christian? Good. So, having some trivial example that you are dealing every day. Okay. So, now we have some terminology in the feedback loop block diagram. Block diagram. Why block? Because we have blocks here. Block diagram. And I'm going to exactly model this in the Simulink of the MATLAB. And I'm going to share the file with it, but over time. Okay. Block diagram. So, based on definition, output of the system, Y of S, over input of the system means the desirable input. This is that one you want to have, and this is the real that's happening right now. Output of the system, output over input of the system, we name it, this is a technical name, closed loop transfer function. TF is for transfer function. Transfer function. What's transferring? Transferring output of the system, real velocity of your car, to desired velocity of your car. Where from time to frequency. I told you transfer function means transferring aerodynamics of the system from time domain to frequency domain. So everything is based on the S, Laplace. So this is closed loop transfer function, and we're going to calculate that. So, guys, So when the output of the system is being measured by sensor, this is sensor of your device. Okay, so it sends the signal out, right? P of S. This P of S is being compared with the X of S. Okay, guys, only now focus on this, all of you. I'm only focused on this part. This part, the sensor part. Sensor part. So I'm taking this out from the block diagram. Say this is B. I'm just cutting, cutting from here and cutting from here. H transfer. This is transfer function of sensor. Transfer function of sensor, H of S. And this is the output of the system, as you see from here, Y of S. So based on transfer function, you saw that this is output over input. So transfer function of the sensor, H, output is which of them? B or Y for sensor? What is input to this sensor? Just use your eyes. What is input? What is output? Yes. So B of S over Y of S. So this is transfer function of the sensor. Okay. If your sensor working perfectly, meaning whatever is going inside without any error sends out, we name this ideal sensor. Ideal sensor has there's no noise affecting on the sensor, only just converting the output to be compared to the input. So if that is, how much it must be? Whatever is going out is exactly as is being. Yes, exactly. If you have an ideal sensor, your BS is your Y of S. Unless you have some noise affecting, like a dust. Suppose that you have a dust in the temperature sensor of your room, just sitting on the sensor, and the measuring temperature is with some noise. See what I'm saying? But typically in this course, we assume that you have ideal sensor, so transfer function is 1. And that's why, for simplicity, for now, I'm saying, okay, if that's the case, the transfer output to the input, here we go. So it's gonna we have, here we go, like that. See what I've done? Because it doesn't change anything. It's 1. Well, your Y of S is B of S. So that's it. We got it? Yes? So, being said that, we have another definition. So, by doing that, by removing the sensor, that meaning that we have ideal sensor, now we have a new name for this block diagram. The name is the same as here, with a small change. This is unity feedback block diagram. Because here is unity 1. The name of this block diagram is unity feedback block diagram. So let me delete these. See what I'm saying? Unity feedback block diagram. Here we go. Okay, this is unity feedback block diagram. And in this course, we assume that our sensor is ideal. So we have a unity feedback controller. So this is first definition that I told you, right? Now the second definition, we name it as open loop transfer function. There is a huge difference between them. Eventually you're gonna learn this in this course. This was closed loop, that is the output over input. Open loop transfer function, guys, is this. So if you want to make it this open loop, you're gonna say, okay, I'm cutting the system from here. It's not being compared. So it is B of S over E of S. See? E comes to B, but we stop here. We're gonna open it. See what I'm saying? It's B of S over C of, B of S over E of S. But you see here that your B is Y. That's right. So you can be, they are the same because this is unit feedback. You can say Y over E. Output over error signal. Open loop transfer function. So before deriving this mathematically, I'm gonna teach you some stupid trivial things. Can I go to the next page? So again, I'm emphasizing closed loop transfer function is the output over desirable input. Open loop transfer, closed loop. Open loop transfer function for this unity feedback is output over E of S. That's it. So because we remove the sensor and unity feedback because your sensor is ideal. That's right. It's one. So see what I'm saying? Yeah, B of S is exactly as Y of S. It's unity feedback. That's right. Yes, there is no sensor in the way. Okay. We removed sensor. It doesn't mean that sensor doesn't exist. It means that your sensor is ideal, measuring perfectly. Okay? See what I'm saying? So, can I go to the next page? Okay, so guys, if you have a signal A going to this operator, plus minus, and a signal B comes here, you know that from kindergarten, the output is going to be A minus B. If you have some blocks like A, B, C, whatever, A, B, C, and this is X, and the output is Y. So X over Y is block A in block B in block C. This is convention in block diagram. So on the other hand, your Y gonna be X in A in B in C. These are two stupid trivial conventions that you have to know. If here you have plus plus, you're gonna have A plus B. Here we go. If you here you have another signal saying C, here's minus, gonna be A plus B minus C. This is just some operator, some minus, and this is the block diagram multiplying. Being said, now look at here. I'm gonna replot our unity feedback block diagram. Okay, plus minus goes to controller, goes to plant. Plant can be car, G of S. Can be robot, can be satellite, can be room temperature, can be the level of the liquid in the tank, can be can be pressure of the tank, can be temperature of the tank, can be electrical circuit that I'm going to teach you in this course. It can be low pass filter I'm going to teach, high pass filter that I'm going to teach, whatever. Okay, anything that has dynamics, differential equation. So this is X and this is Y. So based on whatever I taught you, here is the error signal E of S. Here is B of S or Y because it's unity feedback. Okay. Now, based on definition, if I say closed loop transfer function, I'm just summarizing like this. Closed loop transfer function, based on whatever I taught you, is Y of S over X of S. Okay, good. You see that this is the terminology. Please learn that. Feed forward transfer function. Guys, look at here. This is feedback. Feed forward means look at the block diagram. See only going forward. Only this part going forward. That's right. E goes to C, C goes to G, G goes to Y. This is feed forward path. Feed forward, not block diagram, path. Oh. Feed forward path. Okay. This is feedback path, but this is feed forward path. Based on whatever I taught you here, so you see that Y over error signal is how much? You tell me. Look at this graph. What is Y over E? Is C of S in G of S. Controller block diagram, transfer function to plant transfer function. But we want to find this Y over X. Right? Yes, guys? So on the other hand, from here, you say that Y of S is equal to E of S multiplied by C of S multiplied by G of S. But from this sum operator, you see that E of S is how much, guys? You tell me from this. E of S is how much? Is X of S input minus B of S. And because this is ideal sensor, we know that the B of S is Y of S. So it's enough that I replace this E of S here. Bingo. If I do that, Y of S becomes X of S minus Y of S in C of S in G of S. For simplicity, I drop S because we know that everything is S. Okay. So if you move the y's to the left hand side, your y gonna be 1 factor out CG, and here gonna be XCG. So from here, you simply that the closed loop transfer function for unity feedback block diagram. Oh, what is that? I'm sorry. I plotted this mistake. For unity feedback block diagram, gonna be how much? Y over X gonna be CG 1 plus CG. You just have to know this, not the process. You just have to only know this, because in MATLAB and Simulink you're gonna see this 100 times. And in theoretical things that I'm gonna teach. So for closed loop transfer function is CG controller multiplied by plant divided by 1 plus CG. Okay. So having said, and I told you, can I go to next page? Guys, can I? Yes? Good. So having said, so we got this. Now open loop transfer function is B over E or Y over E. Okay, we got it. Y over E. So open loop transfer function of unity feedback, open loop transfer function is CG. It's CG for unity feedback. Okay. Understood? Yes? Can I go to next page? Where you are talking about? Name it. You're talking about this? So because it says feed forward path means that I'm cutting the system from here and here because this is only forward way. See what I'm saying? This is only forward path. Okay? Yeah. Only going ahead, not being feedback like this. That's the closed loop transfer function. See what I'm saying? Okay. So, welcome. So, now in this course, I'm teaching you the modeling of physical system. So mainly we're going to talk about that. So because of that, we are analyzing the system. I'm removing the controller. Only I have what? The plant itself. We want to see what's happening for the plant. G. So for now, I'm more simplifying the block diagram. We assume that our sensor is ideal. There's no controller yet. We are sending a signal to the plant and being feedback to the system. There's no controller yet. So this is again your E of S. Okay. So by having that, look at here, guys, all of you. Closed loop transfer function is the same except there is no C. Here we go. So it's gonna be your y over x closed loop transfer function gonna be G plant 1 plus G. This is your plant. Okay. And the open loop transfer function gonna be how much? Look at here. There is no C anymore. Controller. Gonna be G. That's it. Because feed forward is this only. Feed forward. Just going forward. Understand? And for the half of the semester, at least, we're gonna work with this. This is closed loop transfer function. This is open loop transfer function. No, you are feedbacking. Closed loop transfer function, you are feedbacking. Open loop transfer function is feed forwarding. Okay? Meaning that we are cutting system from here is not being compared with the X. See what I'm saying? Okay, clear, guys? Okay. Now, but what is important for us as mechanical engineers or control engineers at the end of the day is that we want to make the error signal to 0. We are analyzing the system through this course that when you come to ME530, you can make this happen, error signal to 0. When error signal is 0, look at here, E of S is from this block diagram. E of S based on C is X minus Y. I want to make this 0, meaning that I want to have your Y equals to X at the end of the day. So that's why, based on that, I'm going to introduce you a theory. The name of the theory is the final value theorem. Final value theorem. It says the error signal in time domain when time goes to infinity is the limit of S, E of S when S goes to 0. See, this is frequency domain, this is time domain. At the end of the day, you're gonna care about this. So, guys, your E of S is X minus Y, that's right. Look at here, we said it. So E of S in the block diagram, I'm dropping S. You see here, is X minus Y. But Y here, in this simplified version, there is no control and is unity feedback, is how much based on E and G? Is GE, right? See what I'm saying? Yes, guys? So if I replace the Y here, you get E equals X minus GE. If you simplify everything and factor out E, is 1 plus G equals to X. So the error signal gonna be input over 1 plus plant open loop transfer function 1 over G. Why I'm doing that? Because I'm replacing here final value theorem. It's gonna be Sx 1 plus G when S goes to 0. And using this, we're gonna calculate as a control engineer for linear systems the error signal when time goes to infinity. I said mistakenly. Means steady state value. So we are writing, guys, like this. Bear with me. We are saying, see, S means steady state value. Steady state value. Why? Look at here, guys. I'm going to show eventually in different systems. This is just general concepts. Error signal, time. You as control engineer, you want to have this. Error signal goes to 0. Or you want to have this. Or whatever, based on the dynamic of the system. Or you want to have this. I don't know. So when I say steady state, means this phase. This is steady state. It's final value when time goes to infinity. This is SS, steady state. When I say transient, that you're gonna hear from a million times in this course, means this phase. This is transient phase. Transient phase means vanishing phase. transient phase. So your function, one of your functions, control engineers that make E of t when time goes to zero is zero for the linear systems through this formula. Final value theorem. Okay. So now let me give you one example. Suppose, can I go to the next page? Guys? Yes? Hello? Hello? Guys? Okay. So, this is a real example. Suppose that you have this differential equation, theta double dot plus omega n square theta is equal to omega n square, I don't know, omega n square tau. So, and I'm saying that theta at 0 is 0 and theta dot at 0 is 0. Initial value of these are 0. So what I'm going to do, I'm going to apply the Laplace transform to the both sides. Based on whatever I taught you about the second time derivative, it's going to be s squared theta of s plus omega n squared theta of s equals to omega n squared in tau of s. So theta of s, if you factor out, is going to be s squared plus omega n squared equals to omega n squared tau of s. So, being said, output of the system angle over the input of the system, say, is omega n squared divided by s squared plus omega n squared. So you're going to say how? Suppose this is an impulse. Remember, you are applying an impulse to the pendulum problem. Okay. So this is your closed loop transfer function. Closed loop transfer function, because this is output to the input of the system. Okay. So if I plot this, it's gonna be theta plus 1, gonna be G plant or pendulum, and it's gonna up. Sorry guys. Yeah. So this is tau. Okay. This is theta. And is compared with this. Here we go. Okay, output. So, but I taught you that output over input is G1 plus G. Look at here. Here we go. Output over input. So from here you can find G. How? You can say omega n squared s squared plus omega n squared is G1 plus G. Okay, so you're gonna have multiplied these. If you do that, G of s, I bet $1 million is 1 over s squared. Okay, guys. So you see, you are not putting the closed loop transfer function here. You are putting the open loop transfer function, 1 over s squared. Here we go. This is open loop transfer function, guys. Open loop transfer function. See? 1 over s square. Never put closed loop transfer function here, guys. Never. Here is open loop transfer function. Open loop transfer function. Never put closed loop transfer function. Because you are terminating the block diagram by doing that. Okay? Here must be open loop transfer function. Yeah. What do you mean? What do you mean? I cannot understand you. Please clarify. Again. No, I'm saying that never put this closed loop transfer function. Oh, never put this here. Here must be open loop transfer function. Put it here. If you put like this, look at here, guys. If you put here like this is wrong. Okay. When I give you, or your boss gives you, or you drive closed loop transfer function, and you want to plot block diagram, first you have to find the open loop transfer function, G. No, no. You mean this? You mean this? You mean this? No, never go there. Never. Okay? Understand? State office in the plant? What do you mean? I'm saying that put open loop transfer. Oh my god. I'm saying put the open loop transfer function here. Do not put the closed loop transfer function here. Okay? Do not. See? Oh. Yeah. Always put the open loop transfer function here. Okay? Do not put closed loop transfer function in the block diagram. Put open loop. Yes, block diagram. Yes, in the block diagram. Okay? So, being said, suppose that you are applying the impulse to the pendulum. Huh? Just as input. Okay? Now, can I go to next page? Yes? So, having that, I want to see what's the error signal of that steady state at time when you apply x of s 1 plus g. Because in the error signal also you are putting the open loop transfer function g. See what I'm saying? G. So when s goes to 0. So guys, your x of s in this specific problem is impulse. Your x of s is impulse. So you let me know what is the Laplace of impulse. I taught you. Go to your notes. What's the Laplace of frequency, Laplace of the impulse? How much is that? 1. So I'm leaving here 1. 1 plus g. We derive together the open loop transfer function is 1 over s squared. So 1 over s squared when s goes to 0. So if you simplify everything, you're going to have s cubed in s squared plus 1 when s goes to 0. The answer of this is 0. Means that physically, okay, if this is our pendulum, and if I apply an impulse here, just a huge impact, it's gonna go rotate here and finally back here. See what I'm saying? Yes? The error signal is 0. So if this is here, okay, originally, if you hit the pendulum with a huge impulse force, okay, like as boxing, like right, boom, it's gonna may fly, but at the end, gonna back here. That's right. Yeah. So the behavior of pendulum gonna follow the behavior of the input impulse. Goes back and backs here. So look at here, guys. If I plot it, all of you look at here. This is my impulse. Remember? Right? Huge force at the time 0. Your pendulum, theta of t, gonna follow that. Let me change the color. Here. I'm just putting a little above that to see that, okay? It's gonna be like this and probably gonna be like this. Or, no, actually it's gonna oscillate, say. It's gonna be like this. Yes? Okay? Understand? Hmm? But please keep this in mind because I'm gonna talk about this and about the validity of this 0. Don't ask me why. I'm just telling you. Okay? Understand? Don't ask me why. So this is the error signal. I just wanted to give you the picture of the error signal. Okay? Understand everyone? Yes? Yes, guys? So, having said these general statements that the closed loop transfer function is the open loop transfer function 1 plus open loop transfer function, and the open loop transfer function for this is G without controller and with the ideal sensor. By having this, I'm going to introduce you the next class, the modeling of physical system by math and by Simulink and MATLAB of first order systems. First order systems. What I'm going to do is I'm going to give you the big picture. I'm going to prove to you in 1 week or 2 weeks if you have a spring and damper and you apply a force, dynamically, this is exactly as voltage R resistance capacitor. So it is RC circuit, and this is exactly equals to, I'm going to show it to you in the modeling of physical system in the frequency domain. And this is equal to a tank of the water that you have a flow inside, Q in. Here is the height of the water and the Q out. And you have a resistor here, R of tank, and you have a capacitance here, C of tank. I'm going to show it by MATLAB Simulink and by mathematics theoretically. They are the same systems, and we name it first order systems. When I draw its mathematics, eventually I'm going to model them in the Simulink and MATLAB based on the block diagrams. Okay, everyone? Yes? Clear? Do you have any, okay, do you have any question? And through this, at the middle of that, I'm going to show that this is a low pass filter. Maybe you heard that in industry. This is a low pass filter. I'm going to teach why this is low pass filter. Yeah, but I'm going to show it mathematically why it is like that. Okay, and then I'm going to teach you high pass filter. Only by this high pass filter. And we're going to plot its body diagram, and we're going to go in MATLAB. And we're going to do too many things, guys. Okay? Sure. Closed loop is the output over input. For the unity feedback without controller is G1 plus G, where the G is this is the closed loop transfer function. Closed loop transfer function. This G is open loop transfer function. Here we go. See, you are putting open loop transfer function here to find the closed loop transfer function. You see the difference? Understand? If I plot again, if this is X, G, Y, plus minus. So open loop transfer function you're gonna put here, but the closed loop transfer function is Y over X. See what I'm saying? Yes? And exactly we're gonna do this in Simulink together. This. So this is unity feedback. So because we said that there is no sensor here. Sensor is ideal. So when I remove the sensor from here, so this signal B equals to Y. So this is unity feedback. If you put the sensor here, sir, if you put the sensor here, like as H, you say that no, my sensor has some noise. It doesn't transfer exactly Y to be compared with the X. So B and Y, they are different. So this is not unity feedback. This is only feedback block diagram. Yes. So but when I say that our sensor is ideal, so this is not unity feedback. That's right? See what I'm saying? And we assume in this course that the sensor is ideal. Whatever whatever we are feeding as input to the sensor is sending out. Okay. See what I'm saying? Mm. So this is just mathematics. This is 1 plus, oh, this is 1 plus open loop again. Okay? See what I'm saying? So the open loop is a part of the closed loop transfer function. See what I'm saying? So open loop transfer function is a part of closed loop transfer function. You see? Yeah. Yeah. Okay. Open loop means I'm cutting the system from here and from here. Now this is open loop, that's right. See what I'm saying? Huh? Or I'm saying open loop is this. So open loop means there is no feedback to measure. So that's why, look at here guys. This is open loop guys. Yes or no? Do you see any feedback? No. So this is open loop. So open loop is G, only G. See what I'm saying? Outdoor is G. But when I say closed loop, here we go. We are closing the loop. So now you have to calculate this. It's G1 plus G. Understand? Yep. Yeah. Open loop, closed. And the control engineer is to get feedback from the output to be measured with the input, to measure the error signal, and as controller, based on the error signal, issue a command to your car, to the room temperature, to the height of the tank, to the voltage of the capacitor, I don't know, whatever you say, okay, that behave based on whatever you want. See what I'm saying? What's that? Open, no. Closed loop, that you're making closed loop to make that happen. Okay? Imagine this. You are in front of me, okay? And there is no torque in your joints of body, in your hip joints, the knee joints, in the shoulders, okay? I'm just punching you, and there is no torques in your joints. What's gonna happen to you, do you think? You're gonna fall, that's right? Yes? Okay. But your body has a feedback loop. That's why your joints generate torque. When I punch you, that torque is being regulated that you resist my punch. And that's why you never fall. So if you have no torques in your body, you're open loop. I'm just punching you, you fall. See what I say? Okay? But your body has a closed loop transfer function. I punch you, your brain sends signal to the joints of your body to generate some torques to resist my punch. See what I'm saying? So your body as a human being has a control unit. Get here, guys. As a control unit, this is your brain. This is your brain that sends signals you to your body or joints body here G, and being compared with my input that make the error signal to 0. Okay? And like as your body, we do not want to have systems open loop, because if they're open loop, we cannot control them. That's why we are giving feedback to them, and then we are controlling based on the feedback. See what I'm saying? Yes? Okay, guys, so have fun. See you next week. Okay? Thank you. You too. First, let me